Dr. Shua, can you hear me now?
Yes, yes.
Okay. السلام عليكم ورحمة الله وبركاته. السيد عميد الكلية التقنية الهندسية في ميسان المحترم، زملاء التدريسيين الأفاضل، باحثينا وطلبتنا الأعزاء، أهلا وسهلا بكم جميعا في هذه الورشة العلمية الدولية المقامة برعاية السيد العميد المحترم. يسعدني أن أكون معكم في إدارة وتنسيق هذه الورشة، حيث نستضيف الدكتورة شوا لي سيانغ من جامعة العلوم الماليزية، والمتخصصة في مجال الفيزياء والذكاء الاصطناعي. وعنوان ورشتنا لهذا اليوم هي الإدارة الحرارية في عصر الذكاء الاصطناعي، التحديات والابتكارات والتوجهات المستقبلية. نتمنى لكم جميعا وقتا علميا مثمرا. Hello everyone and welcome to our International Scientific Workshop. On behalf of my son Engineering Technical College, it is an honor to have our Dean, faculty members and researchers with us today. My name is Dr. Ibrahim and I will be moderating today's session. We are absolutely delighted to host our keynote speaker, Dr. Chuah Lee Siang from Universiti Sains Malaysia, School of Distance Education. She is an expert in applied physics and artificial intelligence and made significant contributions to the field of semiconductors. Today, Dr. Chua will be presenting on a very critical and cutting-edge topic, which is thermal management in the AI era, challenges, innovations, and future directions. We look forward to an engaging and highly productive session. Dr. Chua, thank you for joining us today, and the floor is yours. Please, you may start.
Thank you. Okay. Good morning to everyone. Welcome and thank you very much for joining today. Today, I'm going to take you on a journey through on one most pressing and often overlooked engineering challenges of our time. Thermal management in the area of artificial intelligence. We are living in a world where the AI is reshaping the industry, accelerating the scientific discovery, and transforming everyday life. So, behind every large language model and every AI training cluster, GPU power center is an invisible crisis equally building a thermal crisis. That is exactly what we will explore today in the next 60 minutes. Okay, before we start, here is the roadmap of the today discussions. We will start with the AI, computer boom, and the power crisis, and showing why growing the computer demand is creating a thermal bottleneck. Next, we will look at the advanced chip packaging and the thermal challenges, including chiplet and the 3D IC. Then we move to the liquid cooling technology from the direct to the chip to immersion system. After that, we will explore the AI driven thermal management using the model and the digital twins to predict and control the heat. We also will be cover the sustainability and efficiency metric. For example, like the PUE, WUE, and also the waste heat recovery. And after that, we will look at the year 2013, the outlook, and also the physics informed approach shaping the future chip and the cooling design. Let's start. Okay. Artificial intelligence computer is demand has been doubled up roughly every 3 to 4 months, according to the OpenAI. And that means million-fold growth in just a few years. So as the computer scale, so do the power and also the heat. GPU TDP is rapidly increased with AI accelerator project to reach about 2.7 kilowatt per chip by 2026. Today, the AI data center are one of the faster growing electrical load globally, and about 8 to 21% of their power are already used just for the cooling only. So this is no longer a future issue. It is a current thermal bottleneck shaping the entire industry. Okay, before we talk about the solutions, we need to understand why this problem is so critical. From the law, every 10 degrees Celsius increase above the read temperatures, roughly the half semiconductor lifetime. And the thermal stress does not just hurt the performance, it will be accelerate the hardware failure. And that is the thermal trolling, where the GPU automatically slow down under the heat and reducing the performance by 15 to 40%. In practical, you are often getting the far less than the hardware you pay for. Cooling itself is a major cost driven and consumes 30 to 50% of the total data center power in a many fleet. So in a HPC system, thermal issue will remain the leading cause of the unplanned hardware failure. So the important thing is that thermal management is no longer an afterthought. It is a core design constraint that must be addressed at the chip level. Okay, let's make the TDP aspirations concrete. In the
Sorry
2020,
to interrupt you, Dr. Lee, Dr. Shua.
ah,
I think there is some echo in your voice.
is
There
it
is,
possible to off your mic?
yeah, there is some echo. I can hear you, but the voice has some echo. I
I
think you need
didn't
to.
want anything. I tried to off my. Is it now okay?
No, no, same, same.
I didn't on.
Okay, can
I
you
opened
change?
on.
Can you change the source of the voice from, for example, from your mobile phone?
Is it now okay?
Yeah, a little bit better. Yeah, you can proceed now. Thank you.
Okay, thank you. Okay, let's make the TDP escalation concrete. In the year 2020, the NVIDIA A100 was at the 400 watt, and by year 2020, the H100 is reached the 700 watt. So it can be seen that the heat of the temperature is increased. Okay, and to put that in spec, it will be approaching the extremely heat flux conditions on the silicon die, the side of the pump. So it's comparable to the scale that not magnitude to the astrophysical heat intention. So the semiconductor industry is entering a thermally constrained area when the TDP climbing generations after the generations, the performance is no longer limited by the transistor density, but it's the computer architecture. So it will be increased limited by our ability to remove the heat efficiently. And this makes the thermal management one of the most critical challenges facing the chip design, packaging engineer, and the hyperscale data center today. Okay, let's zoom out the rack level where the problem becomes even more severe. For many years, the air cooler rack operates at the 10 to 20 kilowatt per rack. Today, the AI systems are already at the 100 to 200 kilowatt per rack, and the next generation platform like the NVIDIA Rubin Ultra are projected to reach 300 kilowatt per rack. And the key limitations is simple. Air cooling hit a physical wall around 100 kilowatts per rack. And this is not an engineering preference. It is a thermodynamic constraint. The air is very low thermal conductivity, and it makes it impossible to remove the heat efficiently at this density, regardless of the airflow design. And this is why the industry is shifting the decisive toward the liquid cooling, not as an upgrade, but as a necessity. Okay, at the line level, the challenge is highly non-uniform. The model AI chip will see the average heat flux of 100 to 700, but the local hotspot can reach about 2000 and driven by the uneven computer, memory, and also the input-output activity. And the problem is that the conventional thermal interface material can only handle about 550 units. So according to the cooling help reach, single phase cool plate is reached about the 250, while the two-phase system can up to 500, and with the significant engineering complexity. And to manage this, the modern architecture like the NVIDIA and the Intel now include the ambient thermal sensor for the real-time hotspot tracking. And the thermal management is no longer passive. It's become a fully dynamic and data-driven at the line level. Okay, now we look at the challenge. The challenge become a more complex in the chiplet and the multi-die architecture. In the system like the AMD and the Intel multi-late, the power density can differ between 3 to 5 between the chiplets within the same package. And some running the right memory load and another at the full computer stress. And all are just millimeter apart. In a 3D stack design, the issue is even more severe. Heat from the lower tier must pass through the upper layer and creating a vertical thermal bottleneck that works with each aspect. The result is strong thermal non-uniformity with a 30 to 50 temperature difference with a single package. This is why the tools like the ANSYS and also the Celsius are now used for the design stage, and the thermal behavior must be co-simulated and solved before the tap up, not that for fabrications. Okay, let's address the air cooling clearly. At the AI scale, the question, can we just improve the fan? Definitely the answer is no, because of the physics. The air has a thermal conductivity only of the 0.026, while the water is 0.6. So it's roughly 23 higher. That is the fundamental material limit. As a result, even optimized air cooler data center top out around 50 to 80 per rack, while the AI system already require 100 to 200 kilowatt. So the future rack might be over the 1 megawatt. Air cooling is also insufficient. The fan consumes 15 to 20% of the total cooling energy, and the best in the class system is still achieved only the PUE 1.4. The conclusion is straightforward. The air cooling cannot scale to the AI era computer demand. And this is why the industry is rapidly shifting toward the liquid cooling technology. With the thermal landscape in mind, we now look at how the heat actually move through the modern chip package. The dominant architecture is a fixed chip model bonding, where the die is fit and connected to the substrate through the C4 sodium pump. And this improves the electrical performance, but it also defines the thermal path. So the heat flow step by step. First is what we go to the die, TIM1, integrating heat spreader, TIM2, heat sink, and also the final is the cooling system. So each interface will be at the thermal resistance. At the package level, the total thermal resistance is typically zero point 0.1 to zero point 0.3, meaning even smaller interval significantly reduce the junction's temperature. Okay, now we look at the 3D IC thermal challenges. In a 3D, integrated circuit is one of the most powerful and thermally challenging advanced in the semiconductor design. When the die are stacked vertically, heat from the lower layer must pass through each layer above before reaching the heat sink. So each additional layer will be increase the heat bottleneck. And through the silicon vase, this will be helped by moving the vertical copper path through improve the electrical and also the thermal conductions and increasing the effective heat spreading across the site. In practical, even in the modern HBM stacked GPU system, the memory layer can run 10 to 20 hotter than the GPU die due to the limited heat escape. And to address this, the researchers are developing the microfluidic interlayer cooling, advanced TIM, and also the high density TSV thermal network, some of which are already moving toward early the deployment. For the thermal interface material are the critical and often overlooked element in the package level heat management. And they bridge the thermal gap between the component and also the we determine the interface resistance. And we have a two-tab. TIM1 is the high performance interface using the indium alloy. And for the TIM2, the thermal bridge or the phase change material. At the research frontier, the new material are emerging. For example, like the carbon nanotube area, graphite, and also the liquid metal alloy. So another factor is the bone line thickness. Is typically 25 to 75 micrometer, and where the thin layer directly reduce the thermal resistance. So in practice, this TIM perform is depend on the application's precision and on the material property. Now we are moved from the chip to the system level cooling. The most widely used solutions today is a single phase direct to chip cooling, where the liquid cooler will flow through the cooler plate mounted directly on the processor. So the heat will be removed through the force convection and rejected through the heat exchanger. Water is far more effective than the air because specific heat capacity. And this approach is now standard for the 400 to 1500 watt chip. And with the inlet temperature of 35 to 45, is also enable the energy saving free cooling in the many regions. However, the single phase cooling become insufficient above 200 watts per chip, while the required flow rate become impractical. And beyond this point, the industry already shift to the two-phase cooling system, which we will cover later. Okay, two-phase cooling is a fundamental shift in the thermal management and will define the next generation's artificial intelligence AI cooling. Unlike the single-phase system, the cooler in the two-phase cooling boil at the surface, undergoing a liquid to vapor phase change. This leverage the latent heat of the vaporization, which allowing a much higher heat removal efficiency. The impact is significant. To remove a 100 watt and a single phase system may need about 3.5 of flow. So we can see that the two-phase cooling achieves higher performance by using the fluid itself as the heat transport mechanism. Okay, now we look at the cool plate and the key interface between the coolers and also the chip. Their design has evolved from the simple channel to the advanced manifold micro-channel structure. And the main goal is to maximize the removal while minimizing the pressure drop and reducing the both temperature and also the pump power. And the modern design can cut the pumping power by up to 50%. And as the design improves, the thermal resistance drops significantly and directly lower the chip operating temperature. So the material choice is also critical. People are using the copper, aluminum, or the graphite composite. And the major breakthrough is the additive manufacturing, which enable the cooler plate to be tailored to the chip hotspot inlet and delivery the cooling exactly where it is needed. So the cool plates are no longer just a cooling component. They are engineered to match the specific heat and design requirement. Okay, now we look at the immersion cooling. Immersion cooling is take a different approach. Instead of the cooling chip, the entire server is immersed in a dielectric fluid. No fan, no airflow, but just direct the liquid contact. So there have a two main types, single phase immersion and also two phase immersion. So the key vendor is include the GRC, submerged, and also the liquid stack. Beyond the performance, the immersion cooling will be remove the fan, reduce the noise and mechanical failure point, and simplify the system design. Well, require a higher upfront cost and the management is also increasing the attractive for the hyperscale AI infrastructure. Microcurrent cooling is push the heat removal directly inside the chip using an edge silicon channel. So the first show by the Tankernet is achieved up to 790. And in the 3D IC, the microfluid interposer can directly remove the trap between the stack die and also the early AI applications expected around 2026. And the key challenges remain in the manufacturing, reliability, flow control, and is one of the most powerful future cooling approach. AI is both driving the thermal crisis and also helping to solve it. A key example is the Google DeepMind, which will be reduce the data center cooling emerging by 40% using the reinforcement learning and improving the efficiency without changing the hardware. AI is now used in the three main ways: predictions, physics-informed model, and also the fault detections. So in here is from a closed-loop AI thermal control system that continuously optimize the cooling in the real time. Building on the AI control, digital twins can take the thermal management to the next level. A digital twin is a live virtual replica of the data center thermal system and continuously update using the IoT sensor data. So it will be combined the three elements: physics simulation, CFD model, real-time sensor feed, AI-based anomaly detections, and this enable the predict maintenance and fast what analysis, such as the innovation evaluations, new GPU deployment before the installations. And practically, digital twins will be reduce the cooling over the provisionally by 20% and improving the efficiency and design accuracy. The platform, for example, like the NVIDIA Universals, already bringing the digital twins into the production's data center operations and integrate with a real-time HVAC control. Okay, now we look at waste heat recovery strategy. We often treat the thermal output as a problem to the remove, and it can also be viewed as a resource. And up to 64% data center energy input can be recovered as a usable heat. And the key question is whether we can discharge it or reuse it or not. There are the four main pathways for the waste heat recovery. District heating is feeding the heat directly into the urban heating network. Industrial use, supplying 40 to 80% heat for the food processing, and for the agriculture is supporting the greenhouse and vertical farming system. Heat pump, upgrading the low grade heat to the 80 to 100 degrees Celsius for the border use. So the perspective is shifting. The data center is no longer just an energy consumer. It's become the energy hub where the waste heat become a part of the value chain. Closely related to the waste heat recovery, the thermal energy storage, which will help decouple where the heat is produced, when it's used or removed. The phase change material, such as the paraffin wax, sand hydrate, and also the fatty acid, is stored enough energy through the melting and also the solidification between the 20 to 60 degrees Celsius. They act as a thermal buffer, absorbing the sudden heat speed during the AI workload by melting, then slowly releasing the heat as they solidify, smoothing the temperature fluctuations. As the system scales, the chiller water storage tank can shift cooling load to the off-peak hour and reducing the demand charge by 15 to 25%. So looking forward, thermochemical storage offer even higher energy density for the long duration buffering. And overall, the thermal storage link the material science, thermodynamic, grid level energy optimizing into the unified structure for the AI infrastructure. Okay, now we look at the data center. Data center sustainability is now defined as a shared data set of efficiency metrics. PUE, power usage effectiveness, is measure the total facility power versus the IT power. And the older data center range from a 1.6 to 2, while the modern AI facility is target less than 1.2, with a Google averaging about 1.1. And for the WUE, water usage effectiveness, it will be track the water used per watt. And the next generations, the target is less than 0.2, and driven by the closed loop and the AI optimizer cooling system. And for the TUE is overall system usage efficiency, and for the CUE is the CO2 emissions per IT energy, moving toward the near zero renewable offset. So in a short, efficiency is no longer optional. It is now a regulated design constraint. Each AI is bring the new thermal challenge beyond the hyperscale data center. Modular data center is enable the fast deployment using a prefabricated liquid cooler unit. And at the edge, the system must be survived as strictly environment from the negative 40 to positive 55 Celsius, and often with a limited maintenance. So each AI requires compact, resilient, and high robust thermal design. Okay, now we turn to the physics-informed machine learning for the thermal modeling. Physics-informed machine learning is a hybrid approach where the physical law is embedded into the training process. So this to ensure the predictions are not only data driven, but also the physically consistent. And the main advantages is the efficiency. Physics-informed machine learning can achieve accurate thermal predictions with 10 to 100 faster training sample than the standard machine learning, and is a crucial in the semiconductor system where the data is expensive. And the concept is built on physics-informed neural network. Is introduced by the races in the 2019, which can be solved the inverse heat problem from limited sensor data. And in the semiconductor thermal design, applications include the hotspot predictions in a chiplet, fast tau scaling analysis, and the real-time thermal field reconstructions. And in essential, physics-informed machine learning is bridge the gap between the data scarcity and the physical accuracy, is making it increasingly essential for the next generation's thermal code design. Thermal electrical optimizations now essential in the chiplet design because the chiplet have a 3 to 5 power variations layout, and the thermal design must be done together. High power die placed at the package center can overheat, while the displacement is improved heat removal. Design is follow the load, power pack, thermal regulations, flow pack adjustment, and tap out. So the technology, for example, like the TSMC COWOS, is improve the heat spreading and also enable this cold design. So in short, we can say that Thermal and the electrical design must be integrated from the start, not handled separately. Thermal management is no longer just an engineering issue, it's a regulatory and policy concern. In the EU, Energy Efficiency Directive is required the data center above 500 kilowatt to report the PUE, WUE, and also renewable energy usage. At the corporate level, companies, for example, like the Google, Microsoft, Meta, they are committing to the 24 and also 7-day carbon-free energy by 2013. So we can say that the thermal design is a new shape as by the regulations and sustainability policy by the engineering constraint. Okay, looking ahead to the year 2030, thermal management is rapidly scaled with the AI infrastructure. By the 2025 and 2026, two-phase cooling and AI-driven thermal control are the mainstream, and efficiency metrics are shifting from the PUE to the TUE. And by year 2027, microfluoric interposer, they will be enter the productions and the rack density to reach a 300 kilowatt. And for the year 2028 to 2029, microfluoric and and emissions cooling will be expanded to the mainstream deployment. And by year 2013, the rack already over the 1 megawatt with a carbon-free operations and also physics-informed thermal management become a standard practice across the industry. Okay. As we are close, it's important to look at the open research frontier in the thermal management. There are the few key challenges. First is the cow scaling for the 3D IC and the new material, for example, like the gallium nitride silicon carbide and the semiconductor. And the two-phase fluid with a low environmental effect. And for the standardizing microfluoric interface for the heterogeneous chiplet. And the real-time learner digital twins with a sub-second control and the large-scale waste kit utilizations and the sensory storage. Physics-informed agentic AI for the autonomous thermal management. And the thermal powerful design for the post-silicon system, including the neuromorphic and the quantum hybrid computing. So the challenges are deeply interconnected and will need the collaborations between the physics, material science, AI, and the system engineering to solve. Okay, the last slide. We have to cover a wide range of the topic today, from the chip design to the data center regulations. And in here, the AI powered density is rising rapidly, and the thermal management is become the key limiting factor. Air cooling is no longer available above 100 kilowatt per rack, and liquid cooling is needed. Advanced packaging, chiplet 3D IC is required the thermal electrical code design from start. Physics information learning and also the digital twins are shifting the thermal management from the reactive control to the predictive intelligence. Sustainability metrics and the regulations are now the core operational constraint, not optional goal. The future lies at the intersections of the physics, AI, and also the material science. Thermal management may be less visible than computer itself, but increasing will define the limit of the AI revolution. Thank you for your attention, and I'm happy to take a question.
Thank you very much, Dr. Shua, for this
and highly informative presentation. Now we will open the floor for questions from our audience. If you have any question, you may ask directly or write them in the chat box. زملائنا وزميلاتنا الأعزاء عن فقرة الأسئلة، إذا أحد الباحثين عنده سؤال ممكن يسأل مباشرة ويكتب بالشات بوكس حتى تجاوبكم الدكتور. شكرا. Doctor, I have a question. You highlighted that up to 64% of data center power input is recoverable as waste heat. Focusing on applications like direct heat and greenhouse using low-grade heat, 40 to 60, from an average harvesting, from energy harvesting perspective, what are your thoughts on utilizing, for example, thermoelectric generators, TEGs, to directly convert these thermal gradients into electrical energy to power, for example, local sensors array or auxiliary systems within the data center itself?
Okay, what you have mentioned just now, the suggestion, actually I got read before. Some of the people also mentioned so. So, but in the reality, it's not easy to perform the operations. It take time. But I think for the few center, they already studied it already. And for example, like at Malaysia, also currently have an issue. They want to build a data center, and some because we know it, the data center is using a lot of the electric and also the water. Any more question? And currently, the thermal management is not only for the data center. Actually, in the chiplet, AI chiplet right now, is they have a problem. Because right now, when we are using the laptop or all the AI, they need to transfer fast track the information. That's why right now the problem is that when inside there they transfer the data, it will be release the heat. Okay, so currently a lot of the process, even the university also collaborate with factory to handle this type of problem. And another issue is that when the chiplet go to the smaller size, for example, like right now people talk about the 3 nanometer, 2 nanometer, and the traditional simulations to design it is take time. So right now people talk about physics informed AI. So I am believe coming soon the physics informed AI will be very hot. Even some of the university at Europe and also some of the factory, they are starting using this AI to use to produce because original the AI is like a black box. It totally do not understand physics. AI
Uh, okay, good morning. Uh, Sorry, can I have some comment about your valuable lecture?
can.
Okay, sorry, because I cast the lecture just late because
Okay.
I forgot the time. But what I understood from the explanation that there is saving in heat or recovery of heat using the phase change material, right?
Mm.
But here we use they apply such sophisticated technology like AI and other, right? Now I have this question, doctor. You know we are in very extreme climate country. I mean, in summer we have very high temperature outside, outdoor temperature. So can we have the same technology to reduce the heat load? I mean, just to, yeah, you know, I have the reversible idea. I mean, not to save heat, but to get rid of, yeah, extra heat that come from outside using the same technology. I hope that you catch my question, yeah?
Okay, for your case, I think both you need to do the self-study research collaboration with others. I believe different locations, for example, like the Catholic, the Shines, all different. I can say that your temperature there is different with the Malaysia. Okay, so I cannot say your conclusions is applied to your country.
Yeah, in my country, this idea can be applicable in winter, say, that I can save some of the heat through the PCM and to get it stay at night or when I have, yeah, I need extra heat. But in summer now, we have very high temperature, outdoor temperature. So how can I use this PCM to get rid of some of the extra heat come from outside? I mean, is there any idea about this? Because now in our country we think of the outdoor temperature. I mean, we have enough heat to save. So
Okay, for your point, I think
yes,
you can collaborations with a small company. You can suggest this one to your the private company at your country. See, is it any collaborations method? I believe sure got, sure have.
yeah, because you get rid of the heat using the cooling equipment. Now I need the reversible way. I mean, how to get rid of the heat and to absorb this heat, not to make it again. You know, here's the idea. I mean, is there any technology? Because I'm thinking of this PCM to be applied in, yeah, in my mind to have research or to have research team with you and with Dr. Ibrahim and to
Maybe
get
I can start
this idea
later.
because it is very applicable in our country, not in our country, in the whole region of Middle East. You know, you may have idea about how hot the weather is now.
Right now, I do not have any idea.
No
Maybe later
idea.
on, I can go
Never come
deep.
here. You have never
No,
have been here to Iraq or to Arab Saudi.
no,
Okay, I will have a full discussion with Mr. Dr. Ibrahim about this, and we may, yeah, keep in touch with you in the future maybe.
yes,
By
yes.
the way, thank you
No
very
problem,
much
boss.
for your
Yes,
effort and for your valuable explanation.
thank you, boss.
Yeah. Bye.
Okay. Thank you, our dean, for this uh, discussion. And thank you once again, Dr. Shua, for your valuable time and for sharing your great expertise with our institution. Any more questions? I
Hello,
think
Dr. Lee. Can you hear
no more
me? Can you
questions.
hear me? Hello?
Thank you, Dr. Shua, once again, and we truly look forward to attend more excellent sessions and further academic collaboration with you and USM in the future. We wish you all the best. في الختام أتقدم بجزيل الشكر للسيد العميد المحترم على مداخلاته ودعمه المستمر لهذه الورشة، وإلى جميع الزملاء التدريسيين والباحثين والطلبة على حضورهم، ونلتقي بكم إن شاء الله في فعاليات علمية ودولية قادمة لتطوير كليتنا العزيزة. والسلام عليكم ورحمة الله وبركاته. Okay, thank you everyone. Goodbye.